Oh, the derivatives of each one? I got you. So it's like the top and bottom one are negative, and the middle one is positive.
We'll figure out how to.
No? Did you have any questions on homework?
I think I was. Let's go over 61.
Do you know what that is, or you know what page it's on?
That was on 159 to 62. That's what those guys did.
Okay, yeah, this is a tricky one. So we got k prime of 2 is what we're trying to find. And k of x is the f of x to the negative 1 power. And we're given a graph, I think, of f of x. So actually, we don't know that. F of x does something like this. And then we've got a tangent line to f at 2, 5. So that's the point 25, and then we've got a tangent line that comes up. And then we know another point on the tangent line up here that's 2.1, comma 5.3. So we are trying to find k prime of x first. So k prime of x is going to be a chain rule derivative because you have a function raised to the negative 1 power. So its derivative, we're going to start with the power rule, so we'll get negative f of x raised to the, we'll subtract 1 from that exponent and get negative 2, then times the derivative of the inside function, which is going to be f prime of x. So there's our derivative from the chain rule. Now we're going to evaluate this at 2. So we're going to take negative of f of 2 to the negative 2, and then we're going to try to take that times f prime of 2. Okay, so let's see. F of 2 we can tell because the 0.25 is on that curve from our tangent line. Then we know that f of 2 is equal to 5. So this part right here is going to be negative 1 over 5 squared. Now, the f prime of 2 is tricky. That's the slope of the tangent line. So because we have 2 points on the tangent line, we can find the slope of the line between them, and that's going to be our f prime of 2. So f prime of 2 is going to be the 5.3 minus 5 over 2.1 minus 2. That's going to be 0.3 over 0.1, which is going to be 3. And so that's going to be times 3. So we're going to have negative 3 25ths. A lot going on in that problem. Anything else? Okay, we are going to talk about today what's known as implicit differentiation. Oh, did you need that? So this is 3.7, and this is known as implicit differentiation. So what we mean by an implicit function versus an explicit function, let's take something we know. So we'll take x squared plus y squared equals 25. And that's going to be a circle that's centered at the origin and has a radius of 5. So that makes that 0.50 and that 0.05 and so on. So when you have x's and y's mixed together, but we assume or understand that y really depends on x, then that's known as an implicit function. When you separate the y out and you get y equals blah, 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 and everything has x in it, that's an explicit function. So the idea is we can figure out, we're going to figure out a way that when the x's and y's are hopelessly mixed together, that we can't separate them out, but we know that y is still a function of x, we can still find its derivative. Just kind of a crazy idea. So what I'm going to do is I'm going to solve for y here. So this right now, as it's written, is an implicit function because I haven't separated out what y is equal to. But I can in this one. There are most of the time I can't. So, but since I can here, I'm going to separate out the y, and actually I'm going to write it as two explicit functions. We'll get the top half of the circle and the bottom half, so a semicircle and another semicircle. Because the whole circle isn't just a function, it fails the vertical line test, but it's really two functions. So and then I'm going to find its derivative, and we'll find it at, say, 3, because that's easy to evaluate. And then I'm going to come back and show you how we're going to do this with implicit differentiation, that strategy or technique, and see that we get the same thing so you can kind of believe it and trust in it. And then we'll try to see how we can do it when there's no way we can separate out what the y is. Okay? So first I'm going to solve for y. So we're going to get y squared equals 25 minus x squared. We'll square root both sides. And since we want all possible solutions here, we're going to get a positive and a negative square root of 25 minus x squared. So I can think of this now as two separate functions. So we can say one function is going to be the square root of 25 minus x squared. That's the positive part. And the other one, we can think of a second one as being the negative square root of 25 minus x squared. So what we're going to do is we're going to take the derivative of each of those and we're going to evaluate it at x equals 3. So you can kind of see what's happening here. On the picture, you know, the green function here, the positive square root of 25 minus x squared, is that semicircle where all the y values are positive, because what we get out of a radical is always non-negative. And the orange one, the negative of that, is the bottom semicircle, because the radical part is positive, but then it gets multiplied by -1, so all of the y values on that orange one are going to be negative. So that's the semicircle that's below the x-axis. And we're going to see if we can find the derivative, which is going to be, remember, that slope of the tangent line at 3. So we're going to get one answer for the green function and a different answer for the orange function. Then we're going to come back and use what we call implicit differentiation on this thing and see that we get both of those results. Yeah.
What made you pick 3? Is it just like a
I
random?
picked 3 because it works out nice. So it was because when I plug in 3 squared is 9, 25 minus 9 is 16, and that comes out even.
Yeah.
So that's really the only reason. You know, if I picked 1, that would be really awkward because then I get 25 minus 1 is 24. Square root of 24, it just gets more confusing because the numbers aren't so nice. That was my only reason for that. Okay? All right, so let's do the green one first. So we're going to find this derivative. So we are going to say dy dx. And now this is a chain rule derivative because you have the 25 minus x squared whole thing to the 1/2 power. So to do the chain rule, we're going to differentiate the outside function first. So how does that look?
Bring the 1/2.
So 1/2 good comes in front. We leave the 25 minus x squared as it is. Raised to the good, because we're subtracting 1 from that exponent. Now here comes the chain rule part, times, and the derivative of the inside is -2x. Very nice. Okay, let's do some cleanup here. So we can see that the 1/2 and the 2 are going to cancel. I'm going to leave the negative x, and I'm going to move this negative 1/2 into the denominator. So it's going to be a negative x over, and then that 1/2 is going to make it the square root of 25 minus x squared. So that is our derivative of that top semicircle, the green one. Now let's just evaluate that at x equals 3. So when we plug in 3, then we're going to get, I'm going to switch to prime notation. That just works a little easier. on the evaluation part. So I'm switching from the dy dx to f prime. And if we plug that in, we're going to get a negative 3 in the numerator. In the denominator, there's the 3 squared, which is 9. 25 minus 9 is 16. Square root of 16 is going to be 4. So that is going to be a negative 3/4. Okay? Now I'll come back and do the orange one. So on this one, the dy dx, it's again chain rule, almost the same thing, except we have that extra negative in front. So that's going to look like what? Good, there's a negative 1/2. 25 minus x squared raised to the negative 1/2. And here's the chain rule part again. We're going to get a minus 2x again. There's our negative 2x. This time, the 2.5 cancel, but so do the negatives. So we're just getting an x in the numerator. And that negative 1/2 power is going to move that into the denominator and be a 25 minus x squared in the denominator. So just like we got for the first one, the green one, except that it doesn't have that negative sign. So again, we're going to evaluate this at 3. So for this function, we're getting 3 in the numerator. And again, 25 minus 9 is 16. Square root of 16 is 9. Or square root of 16 is 4, rather. So we get 3/4 for that one. Okay? So this, now what we did here is we made the x squared plus y squared equals 25 into 2 explicit functions. They're explicit because we could get y by itself, all of the x stuff on the other side of the equal sign from the y. Now I'm going to come back and show you what we do with implicit differentiation. And so I am not going to separate out the y, but I'm going to go right to where we have this here. And so what we're going to do is just, as it sits, we're going to take the derivative with respect to x. Now, we know how to differentiate x squared, that's old news. But when we get to the y squared part, to differentiate that, we have to think of that as being a function to the second. And so it's a chain rule derivative. You have a function, even though we can't say what that is, but it's a function to the second. So we're going to differentiate the x squared part and then times the derivative of the inside function, which we don't know. So we're just going to name as y prime. Let's see what that looks like. So the derivative of x squared is 2x. Now, this we're treating as a function. So you're thinking of that sort of without writing it this way. It's some unknown function to the second. So the chain rule derivative is we're going to go 2 times that function to the first, and then times the derivative of the inside function. That's our chain rule. But we're not going to call that prime. We're just going to call it y prime. So we're going to get 2 times y to the first, and then the derivative of y, I don't know what it is, I'm just going to call it the symbol y prime. And then on the other side of the equal sign, the derivative of a constant is 0. Now, what we're going to do here is try to solve for y prime. That is our derivative. So when we do that, we're going to get, I'm going to leave the y prime term on the left, and I'm going to move the 2x to the other side of the equal sign. So we're going to subtract that over. Still trying to solve for y prime. So we are going to, I'm going to create a little space here. I don't think I really need that anymore. So I'm going to divide by the 2y and get y prime is negative 2x over 2y. We can cancel the 2's and call it y prime is negative x over y. Okay, so far. Now, when we plug in the number, we said x was 3, but we didn't give a number for y. So what we're getting then is y prime is negative 3 over, but we have to solve for the y back in the original equation when x is 3. With me? So the 3 squared is 9, plus y squared equals 25. We subtract the 9 over, and y squared is 16. When we square root 16, we want all possible solutions. So we're going to get plus or minus 4. This is how we're going to still get 2 different answers out of this one derivative. So when x is 3 and y is positive 4, we're going to get the negative 3/4. And that's what we got on the green function. When we use the y equals negative 4, then we're going to get that y prime is negative 3 over negative 4. That's the 3/4, and that's the slope we got on the second one, the orange one. That make sense? So it's kind of crazy, but and we're going to see somewhere it gets much more complex than this. But the idea behind it is we don't have to be able to separate off the y and write an explicit function in order to find its derivative. Okay, so let's see how life gets more complicated. Well, maybe I should have said, just as a point of interest, here's, I'm going to recreate that. There's our x squared plus y squared equals 25. And we said that y prime was a negative x over y. So out of curiosity, had we chosen x to be 0, what would the slope of the tangent line be then? Yeah, because you plug in 0, it would be 0. Well, does that match with what we see there? When x is 0, you see that the tangent line would have been that horizontal line and its slope is going to be 0. Even more interesting, what if we had tried to find the slope of the tangent line as x equals 5? It's going to be a vertical tangent. Well, how do we get this y value?
0.
Plug the 5 in here, right, so you see it, 5 squared is 25. So if we plug in and solve for the y, we're going to get that y is 0, and that's going to make our derivative undefined, which is what's happening when we have a vertical tangent at that point, which is what happens at x equals 5. Does that make sense? Okay. Interesting thing to see. Okay, so let's see where we want to go with this. Let's see how bad it can be. I'm going to throw you right into the wolves here, because I want to make sure we can do some really complicated ones. And I don't want to save them all for the end, and then I get to do the really hard stuff. So I tried to warn you, here it is. There we go. So from very simple, a nice little circle, to who in the world knows what this is even. Okay. Now, our goal, remember, is to try to find out what y prime is. That's the derivative. So we're going to take all the derivatives of these things, and we're going to have to use all the different rules. There's going to be, we're going to have some chain rule derivatives. We're going to have to remember how to differentiate a trig function, a logarithm, an exponential. We're going to have a product rule here. We're going to have to remember what to do with this. Okay, so a lot going on. Okay, let's see what happens. So first of all, this one. This is a chain rule derivative with a product inside. So we're going to take the derivative of the outside function, leave the inside function alone, times the derivative of the inside function, which is going to involve a product rule. See the groundwork? Okay, derivative of cosine is? Negative sine, nice. And we leave the xy there. Times, we're going to take the derivative of the inside function, which is the product of x and y. Tell me if I'm going too fast. So we're going to take the first times the derivative of the second. So that's x times the derivative of y, which we're going to call y prime, plus the second, y times the derivative of x, which is just. Now, we're going to come back to this in a minute, but I just want to point out, what's going to happen here is that because you have, in this bracket here, you have one term that's got a y prime in it and one term that doesn't. So what we're going to do ultimately is we're going to have to distribute this. We're going to gather all of the y prime terms on one side of the equal sign. We're going to move anything that doesn't have a y prime in it to the other side. Then we're going to factor that y prime out that we're trying to solve for, and we'll divide all the other mess to the other side. That's kind of going to be our strategy here. Okay, we'll come back to that. Now we've got a logarithm. So do you remember how to take the derivative of a logarithm?
So derivative the inside over the du
du over u, nice. Has been watching videos. That's encouraging. So it's going to be 1 over u du or du over u either way. So what we see in the logarithm goes in the denominator. Its derivative goes in the numerator. Its derivative is derivative of x, which is 1 plus y prime, right? Because the derivative of sum is the sum of the individual derivatives. Now here again, we're going to have to come back because you have one term that doesn't have a y prime and one that does. So we're going to have to separate these into two separate fractions because the y prime term is going to stay. The non-y prime term is going to have to go to the other side of the equal sign. We'll get to that. Equals. Now we got e to the u. So the derivative of an exponential base Euler's number is
e to the x minus y and times the derivative of the exponent.
exactly. So e to the u times du, the derivative of the exponent, which is good. And the derivative of x minus y is going to be
1 minus y prime.
excellent. And again, we're going to have to distribute that because the 1 doesn't have a y prime, but the y prime does. They're going to go on different sides of the equal sign ultimately. Now, the next one is a little tricky. There's kind of two ways you can think of this. Some people will just attach the negative to the 3 and do a product rule where the first is the negative 3x and the second is the y. Other people will just factor that negative out and then go first is 3x times then the second is y. Any particular option you like? Factor out the negative? Okay. More people like that too. I don't know why that is. That wouldn't have been my choice, but that seems to be what everybody else likes. So there's the minus. Now we're going to differentiate the 3xy using a product rule. So we got the first, which is 3x times the derivative of the second, which is y prime, plus the second, y, times the derivative of the first, which is 3. All done. Okay? And let's see now, the derivative of pi to the third, which is going to be, yeah, trick question. It's just a constant, so its derivative is 0. Nice. Okay, now, calculus is done. Algebra is just beginning, so we have a lot of distributing to do. So we're going to take this times the xy prime. I'm going to put that right then in front, so it doesn't look like that's somehow in the sign. So I'm going to go negative xy prime sine of xy. And then the y is going to hit that. I'm going to do the same thing. I'm going to bring the y to the front. So that's going to be a minus y sine of xy. We're going to pull apart this fraction. So we're going to write it as 1 over x plus y prime over x plus y. That making sense? Okay, and here's our equal sign. Now we're going to distribute that e to the x minus y. E to the x minus y times 1 is just e to the x minus y. E to the x minus y times the minus y prime is going to be a minus. I'm just going to bring the y prime in front. E to the x minus y. And then we'll distribute that negative sign, so it'll be a minus 3xy prime minus 3y. Okay, we're making progress, believe it or not. Now, all the terms here have been separated. Some have y primes, some do not. Now, you can go either way with it, but I'm just going to choose to bring all the y prime terms to the left, and anything that doesn't have a y prime, we're going to push to the right. Okay, so let's see. This has a y prime. It's going to stay where it is. Xy prime sine of xy. The minus y sine xy, there is no y prime. I'm going to add it to the other side. So that's going to be a y sine of xy. It gets moved to the other side of the equal sign from the y primes. The 1 over x plus y, there is no y prime. It's going to get moved to the other side. So we'll subtract it, it's a minus 1 over x plus y. The y prime plus x plus y has a y prime, it's going to stay on this side, so I'm writing it as plus y prime over x plus y. I've taken care of everything on the left, they've sorted them out. Now I'm moving to the right side of the equal sign. E to the x minus y doesn't have a y prime, it's staying put on the right side. So that's going to be now plus e to the x minus y. Here's now a y prime term, a minus y prime e to the x minus y. We'll push it to the left side, so I'll add it over there. So it'll be a plus y prime e to the x minus y. The next term, 3xy prime, does have a y prime. I'm adding it to the other side. That's a plus 3xy prime. And the minus 3y doesn't have a y prime. It stays where it is on the right side. Now we've sorted them. Everything on the left has a y prime. Nothing on the right has a y prime. So all of these that have y primes, we're going to factor that y prime out. So that's, I think, a negative x sine of xy plus, what's this going to become, this fraction? Good, just 1 over x plus y, nice. And then an e to the x minus y and a plus 3x and the parentheses. Okay, now all this stuff in the brackets is multiplying the y prime. So we are going to divide it all to the other side. I'm going to be a little bit on the lazy side here. So I'm going to divide all of this stuff here by that negative x sine of xy plus 1 over x plus y plus e to the x minus y plus 3x. And that is our derivative, that whole big ugly fraction. Now that was ridiculously complicated just because I wanted to get a chance to see essentially all the different complications we can get there. Not all of them probably, but most of them. Because we've seen what happens with a trig function, with a logarithm, with an exponential, with a product rule, with something that's going to be a chain rule derivative there. And I don't want you to do any kind of simplification there. Don't try to get the x plus y's out of the denominator. That's not the point of this. The point is just to get there. Now, anytime you do one of these, some people will choose to bring the y primes to one side. Others will choose to bring it to the other. That's fine. Your answers will be the same, except they will be, if you move the y prime to the other side, then everything would be the opposite sign as this. That is, it'd be what you would get if you multiplied top and bottom by -1. That's equivalent, so we're still agreeing. Okay, well, that was fun. Let's do a tangent line question. And maybe even a concavity question. Let's see, let's find y double prime for our implicit function 2x cubed minus 3y squared equal to 8 at the point 2, 4. Much simpler here. So we're going to first find y prime, and then we're going to do it again to find y double prime. So here we go. Derivative of 2x to the third is? Good. And now minus 3y squared, we've got to be thinking chain rule derivative. So that's going to look like what?
2.
So 2 times the -3 is going to be minus 6. Y to the first times the derivative times y prime, the derivative of that inside function y. With me there? Evan?
Yeah, I think I got it.
Okay. And the derivative of 8. Okay. Progress. We're gonna solve for y prime, so anything that doesn't have a y prime, we're moving to the other side of the equal sign. Negative 6y y prime is a negative 6x squared. Solving for y prime, so we'll divide by the negative 6y. And if we simplify that, the negative 6's drop, and we've got x squared over y. Okay, so I'm going to put a box around this so I don't forget where we left it. Now we're going to differentiate this to get y double prime. So I'll do the left side. The derivative of y prime is y double prime. You're going to have to do the right side, and what rule are we going to have to follow here? Quotient rule. So we have the denominator, good, times, which is, keep going then, good, numerator times the derivative of the denominator, which is y prime, good, all over, very nice. Okay, now all we have to do is evaluate this at x is 2 and y is 4. What are we going to do about this y prime? I think we're going to have to figure out what number is y prime when x is 2 and y is 4. See it? Well, let's go ahead and do that. So y prime is going to be 2 squared over 4. Well, this was carefully constructed. It's just 1. Okay, so our y double prime is, let's see, the y is going to be 4. 2 times 2 is going to be another 4. Minus 2 squared is yet another 4 times our y prime we said was 1. On the bottom, y squared is 4 squared. So that looks like 16 minus 4 over 16, which is going to be 3/4. So one question that might be asked is this curve concave up or concave down at the point 2, 4, to which you would say because f double prime, the second derivative is positive. So we could answer the question about concavity. Nice, 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 nice. Okay, let's see if we can do a tangent-like question. Stuff we've done in the past with simpler functions. So let's see if we can, let's see. So find the equation, find an equation of the tangent line to the curve y cubed minus xy equals negative 6. And I'm going to say at x equals 7. And I don't know if I have to tell you why or not. Probably so. So I'll say y is 2. So there's our point at 7, 2. We're going to try to find the equation of a tangent line. So to find an equation of a line, we need, what things do we need? Derivative so we can get slope, and a point, and we already know the point. Okay, so our point is going to be 7, 2. Now we got to find the slope, which is going to come from the derivative. So here we are again. We're going to do some implicit differentiation. So the derivative of y to the third is going to be, very nice, 3y squared y prime. Now be careful, here's a product rule again with a negative in front. So we're going to do that same strategy of leave the negative out. And now do our product rule on x times y. So let's see, product rule means, okay, so that's x times, good, keep going. And the derivative of x is just and our derivative of negative 6 is? Okay, we'll distribute that negative sign. So we got a 3y squared y prime minus xy prime minus y equals 0. You want to keep the y prime terms on one side and move the non-y prime terms to the other side. So we'll keep the 3y squared y prime minus xy prime. We'll add that y to the other side. We can factor out the y prime, which we'll leave behind. Good. 3y squared. Nice. Good. So our y prime is going to be y over 3y squared minus x. Now we're plugging in the numbers because we were trying to find a slope, which is going to come from our derivative. So let's see, y is 2. We have 3 times 2 squared is 4 minus the 7. So that's going to be 12 minus 7 is 5. We got a slope of 2/5. That sounding right? And we had our point was 7, 2. So our tangent line is going to be y minus y coordinate. 2.
2/5 times x minus 7.
Nice. Good to go? Oh, what else can I ask you to do here? Can I ask you on the same one, when does this have a horizontal tangent? When does y have a horizontal tangent? How would we know that?
Say equal to 0.
Yeah, so that's the derivative equal to 0.
Yeah.
So what is going to make our derivative equal to 0? When is a fraction equal to 0? When its numerator is 0. So really, all we have to say here is what must be true. Y equals 0. Now, that's part of a point, right? That's the y coordinate of maybe a point. How are we going to find its x coordinate? Plug it into where? The original, yeah, because points are going to come from the original. If we plug in 0 for y, what do we get?
X equals 6. Oh, no, yeah.
Yeah, we're getting 0 equals negative 6, right? That's not true. What does that mean? Yeah, that means there's no point on that curve with a y coordinate of 0. And if that's the case, there is no horizontal tangent. Okay, follow how that works? Okay, so even though it looked like you had something there when you had the y equals 0, we would have to be able to get an ordered pair to go with it, and it doesn't work. Okay, so let's ask another question. How about, are there any vertical tangents? How do we answer that question?
The denominator is 0.
That's where the denominator is 0, because a vertical tangent is going to have undefined slope. So we can try to set this 3y squared minus x equal to 0. Let's see. I guess that's going to mean, I'm not sure where we're going. I can add the x to the other side, right? And say x must be 3y squared. Is that okay? Well, if we go back to our original, where is that gonna take us anywhere meaningful or not? So if we plug in 3y squared for the x, you with me there? So we would get, let's see, y cubed minus 3y cubed equals -6. What's y cubed minus 3y cubed? Negative 2y cubed equals -6. You divide by the -2, you get y cubed is equal to
Minus 3.
3. So y would be cube root of 3. Let's see, I think we had x was over here, right? So we could say x is going to be 3 times the cube root of 3 squared. What's the cube root of 3 squared? Tough question. If I asked you a question, if I said, what's the square root of 2 times the square root of 3, you would say, because you can multiply the inside, that's square root of 6. So this is, the cube root of 3 squared is the cube root of 3. Yeah, exactly, it's going to be the cube root of 9. So that's going to be 3 cube root of 9. Well, that's a weird number, but it's a number. So it looks like at, what did we say, 3 cube root of 9, comma, cube root of 3, this curve is going to have vertical tangent, because that's going to make the denominator 0. Kind of crazy? Kind of crazy. All right. Wow, you guys, I can't believe we got through all this. Well, I think we're ready to come to the board and see if we can do something challenging here, because I think we've got everything covered that we need to. And if we can do this, then maybe we can do some practice for tomorrow's test. So let's do x cubed minus y cubed minus 4x squared y equals 11. And let's just see if we can find y prime. I'm going to pause this here while we work on it. Okay, I'm going to work this. These guys already got it, so I'm going to see if I can get their same answer. And then we're going to work on a practice problem for tomorrow's test. And the suggestion was don't use the quotient rule on this one. So here we're going to get 3x squared minus 3y squared y prime. This is going to be a product rule. So we have the first times the derivative of the second plus the second times the derivative of the first. And the derivative of 11 is 0. So that's going to be 3x squared minus 3y squared y prime minus 4x squared y prime minus 8xy equals 0. So I'm going to add the y prime terms to this side so we can make them be positive, although you don't have to do it this way. The y prime terms are going on one side, and the non-y prime terms are going to the other side. We can factor the y prime out here, and I think that is going to be that. And then we can divide that over. So we'll get our 3x squared minus 8xy all over 3y squared plus 4x squared as our derivative. I'm going to give this one a shot. So we're going to split this up, and I think that is to the 1/2.
Well,
and minus 1 that way,
Right.
and that way.
Oh, yeah. Right.
We can subtract x, oh, sorry, this is still f, I haven't taken the derivative yet. We'll subtract exponents, and subtract exponents, and see that as a negative exponent. And we can take our derivative. So we'll be using a power rule, 3/2 x to the 1/2, and minus 2x to the negative 1/2, and minus 5/2 x to the negative 3/2. We in agreement? Score. You okay with that?
Yep.
Okay, you guys looking out for Evan, or just letting him twist on his own there? Let's do,
so you don't really wanna do the quotient rule, you just split up the fraction, so. X squared over. And then you got it.
this is our product rule, first times the derivative of the second, which involves a chain rule, plus the second times the derivative of the first, little cleanup. Second derivative, another product rule, first times the derivative of the second, plus the second times the derivative of the first, another chain rule. Simplify, factor, e to the 2x is never 0, so x must be, okay, I got to set it equal to 0 and solve, you're almost there. Okay.